Draw a square, 1 unit on each side. Now draw its diagonal. That line is real. You can see it, you can trace it with your finger, you could cut along it with scissors. So here's a question that sounds almost silly. How long is it? 2,500 years ago, that innocent question broke mathematics. Because the answer is a length that exists. And yet no fraction, no ratio of whole numbers, no matter how clever, can ever measure it exactly. This is the story of the first impossible number, and of the proof that forced everyone to believe in it. This is Symmetry. Let's find out why. It starts in a world where everything was made of whole numbers. The Pythagoreans believed something beautiful. All is number, and by number they meant the counting numbers. 1, 2, 3, and their ratios, and honestly, they had good reasons. Pluck a string, then pluck one exactly half as long, and you hear the same note, 1 octave higher. A ratio of 2 to 1. Make it 3 to 2, and you get a perfect fifth. Music itself seemed to obey whole numbers, so they pictured every possible length the same way. Lay down a grid of whole number steps, and any length you could ever need would be some number of steps, divided by some other number of steps. 3 over 2, 7 over 5, a ratio, always a ratio. And here's what made that belief feel unbreakable. Fractions are everywhere. Take any 2 fractions, as close together as you like, and there is always another fraction strictly between them. Halfway between them, for a start, and another between those, and another forever. The fractions form an infinitely fine dust that settles into every crack of the number line. If you needed a length just a hair longer than 1.4, a fraction was waiting there for you. It seemed obvious that the fractions filled the line completely. There simply wasn't room for anything else. Every point had a name, and every name was a ratio. What could possibly be missing? The Greeks even had a physical picture for this faith. Take any 2 lengths, 2 sticks, 2 ropes, the side and the diagonal of a temple floor. They believed you could always find some small common unit that measures both of them exactly. Maybe it fits 5 times into one stick and 7 times into the other. Then the 2 lengths stand in the ratio 5 to 7, and the little unit is their common measure. For lengths built from whole numbers, this always works. You can even hunt the biggest such unit by stepping the shorter length along the longer one, over and over. 2 lengths, 1 shared measuring stick. That, to a Pythagorean, was what it meant for the world to make sense. Keep that picture. It's exactly the thing that's about to die. Then someone asked about one specific line. Take the simplest square imaginable. Every side has length exactly 1. Now draw the diagonal, corner to corner. The diagonal cuts the square into 2 identical right triangles, and that means the theorem of Pythagoras applies, the one we proved on this channel. The square on the diagonal equals the sum of the squares on the 2 sides. 1 squared plus 1 squared. That's just 2. So the diagonal is the number which, multiplied by itself, gives exactly 2. Today we write it as the square root of 2. The Pythagoreans didn't have that symbol, but they had the length itself. It was sitting right there, drawn on the ground in front of them, asking to be measured. So the hunt began. Find the ratio. Try 1.4, which is 7/5. Squared, that's 1.96. Just short. Try 1.42. Squared, that's 2.0164. Just over. Squeeze tighter. 1.414. Squared, 1.99962. Achingly close, still short. Each new decimal traps the target in a smaller cage, and there's always a fraction inside the cage, ready to volunteer. But notice the thing that never happens. The square never lands on 2, exactly on 2. Every candidate grazes the bullseye and misses, like an archer cursed to hit everything except the center. And some of those misses were so close, they felt like a taunt. Look at 7/5 properly, because it's a beautiful failure. If 7/5 were exactly the square root of 2, then 7 squared would have to equal 2 times 5 squared. Count it out, square by square. 7 squared is 49 little squares. 2 times 5 squared is 50 little squares. 49 against 50, off by exactly 1. One single unit square out of 50 is the entire difference between a tidy rational universe and a broken one. You can almost hear the Pythagoreans muttering, "So close." Surely a better fraction fixes this. So they hunted bigger, 99 over 70. Now 99 squared is 9,801, and 2 times 70 squared is 9,800, off by 1. Again, go bigger still, 577 over 408. Squares in the hundreds of thousands now, and the two totals miss each other by exactly 1. Again, the pattern is eerie. The best fractions don't drift randomly around the target, they orbit it in a perfect rhythm of near misses, always 1 unit away, no matter how enormous the numbers grow. When failure is this systematic, it stops looking like bad luck. It starts looking like a law of nature, and a law demands a proof. So instead of hunting the fraction, they set a trap for it. Here's the move, and it is one of the most powerful ideas humans have ever had. Stop searching. Instead, assume the thing you're hunting exists and follow what its existence would force to be true. If the consequences explode, the thing was never real. So suppose the square root of 2 really is a fraction. Call it p over q and add one crucial condition. Reduce the fraction fully first. 6/4 becomes 3/2. 10/6 becomes 5/3. Cancel every common factor until nothing is left to cancel. That's always possible, and it leaves p and q sharing no common factor at all. Hold on to that little fact. It looks like housekeeping. It is actually the tripwire of the whole trap. Now do the only algebra this proof needs. If the square root of 2 equals p over q, square both sides. 2 equals p squared over q squared. Multiply both sides by q squared, and you get the whole story in one line. P squared equals 2 times q squared. Read that line slowly, because it's the hinge of everything that follows. P squared is 2 times something. 2 times a whole number, and any whole number that is 2 times another whole number is, by definition, even, so p squared is an even number. That's not an estimate, not an approximation, not a guess. It's forced the way a locked door forces you back. And now the whole proof comes down to even against odd. Here's a small fact you can build with dots. Take an odd number and square it. Arrange the dots into a square grid and try to pair them off 2 by 2. An odd number is some even part plus 1, and when you multiply it by itself, every piece pairs up cleanly except one lonely dot in the corner. One odd dot left over always, so an odd number squared is always odd. Now flip it around. An even number is 2 times something, so its square is 4 times something. Even automatically with room to spare. Squaring never changes a number's parity. Now apply it. We know p squared is even. If p were odd, p squared would be odd. It isn't, so p cannot be odd. P itself must be even. But watch what that triggers. If p is even, we can write it as 2 times k for some whole number k. Put that back into our hinge equation. P squared becomes 4k squared, so 4k squared equals 2q squared. Divide both sides by 2, and the equation hands us something familiar. Q squared equals 2k squared. Look at the shape of that line. It's the same sentence as before, with the letters shuffled. Q squared is 2 times something, so q squared is even, and we just proved with dots what evenness of a square means. Q must be even too. The argument has started eating its own tail. Now the trap snaps shut. P is even. Q is even, then both are divisible by 2, they share a common factor after all. But go back to the very first thing we did. We reduced the fraction fully, and we were entitled to, because every fraction has a fully reduced form. We guaranteed that P and Q share no common factor. Both statements came from pure, careful logic, and they cannot both be true. When flawless reasoning produces a contradiction, only one thing can be at fault. The assumption we fed into it. There is no fraction p over q whose square is 2. Not 7/5, not 99 over 70, not any ratio built from whole numbers anywhere, ever. The diagonal is real, and it lies beyond every fraction. So what exactly broke that day, and what was born? There's an even more haunting way to see the same collapse. Suppose a fraction for the square root of 2 existed. Our argument shows both its numbers are even, so you can have them both and get a smaller fraction that works just as well. But then that smaller one has the same property, so you can have it again and again, forever. Each step, a genuinely smaller pair of whole numbers. But whole numbers cannot shrink forever. Below any whole number, there are only finitely many steps down before you hit one. A staircase that must descend forever, built inside numbers that cannot, is impossible. Mathematicians call this infinite descent, and it kills the fraction from a completely different direction with the same verdict. And here's what it means for the number line. The fractions really are an infinitely fine dust. That part was true all along. But dust is not a solid. The point at the square root of 2 is a hole in that dust. No fraction sits exactly there, no matter how deep you zoom. And once you know one hole exists, they appear everywhere you look. The square root of 3, the square root of 5, pi, e. In a precise sense that later mathematicians made exact, almost every point on the line is one of these holes. The rational world the Pythagoreans trusted turns out to be the thin film. The irrationals are the ocean underneath. The proof also leaves a fingerprint you can actually see. Write the square root of 2 as a decimal. 1.41421356, and on it goes. If those digits ever fell into a repeating loop, the number would secretly be a fraction. There's a standard trick that converts any repeating decimal straight into a ratio of whole numbers. So our proof forces the opposite. The digits of the square root of 2 never end and never settle into any repeating pattern, no matter how many millions of digits you compute. Irrational doesn't mean unreasonable. It means, literally, without ratio. And you just watch the reason why. Legend says the discovery belonged to Hippasus of Metapontum, and that the Pythagoreans were so shaken they drowned him at sea for revealing it. The story is probably myth. But the shock was real, because this was the first time in recorded history that pure logic overruled belief, intuition, and authority all at once. Nobody wanted this result. It won anyway because the proof left no exit. And that is the real inheritance of the square root of 2. Not just a new kind of number, but a new kind of argument. Proof by contradiction. Assume, deduce, explode, conclude. Mathematics has trusted that weapon and used it daily for 25 centuries since. So the diagonal of a 1 by 1 square is a length you can draw with a straight edge, and still no fraction will ever name it. Mathematics didn't collapse when that secret came out. It grew up. If this gave you that small jolt of, oh, that's why, then that's exactly what symmetry is for. Subscribe, and every week we'll make one more piece of math or science click. And if it did click, a like helps this find the next curious person.